I'm going to go through an example, I'll introduce it on the computer, of how we apply Fourier series to vibration problems, okay? If you've got a mass spring damper system, a linear system, then the equation is going to look like this. It's for a single degree of freedom system. Yeah? Where f of t is the forcing function. Now, if f of t is a non-sinusoidal periodic function, then you can use Fourier series to obtain the steady state solution. So here we're looking for the xpi bit. We're not worrying about what's happening with the with the transients to start with. We're looking at what happens as time goes to infinity. So the steady state solution. So the particular integral bit is what we're interested in here. And it's worth remembering that you can superpose solutions on top of each other to get the complete solution. So here, we know that f of t is going to be a sum, okay, of different forces at the different harmonics in a sense, okay, f of n, t, as n goes from 1 to n, or infinity. If you've got different forces, there's going to be a response for each of those forces, which is going to be x of n. So if we have here we've got a force that represents some, well, taking the example from last week, if you remember we had an offset sinusoid. And the solution for that offset sinusoid was basically the solution for a constant force, which is the offset, and the solution for the sinusoid added together. Well here, if we've got f of n, f of 1 times t is the constant term, and f of 2 is the sinusoid, then the solution is going to be the solution for the constant term and the solution for the sinusoid added together, the sum of those two solutions. And so you can apply the same logic with Fourier series, because here we can solve for the force, you've got the Fourier series is made up of sines and cosines, okay? So each of those sine or cosine terms will be one force. And so you can solve for each of those forces and then add up those solutions to get the complete solution. Okay, so it's the same principle being applied. So that's what we're going to do. So x of n is a function of time, okay, the displacement resulting from f of n, that force that's being applied. And if you've got big N number of forces, you're going to have big N number of solutions, and you basically add them up to get x of t. Okay? That's the superposition principle, and that's what is being applied here. So there's a three-step process to solve these problems. You first off need to find the Fourier series of f of t, if it's not given to you already. It may be given to you. We don't know. Okay? So you've got to find the Fourier series of f of t. Then you need to solve that differential equation. Okay, so if f of t is, I don't know, f0 sine of omega t or whatever, you need to solve for that solution, okay, x of n, for that corresponding nth harmonic in the Fourier series. And then obviously, if there's a constant term, you need to solve for x0, okay, if any in the Fourier series. And so you get xn and x0. And then you superpose the solutions obtained to give the overall steady state motion. So you've got your solution to the constant term plus a number of terms that you add together. Obviously that number of terms would be infinite if you've got infinite number of terms. Here we've just said n terms. So that's how you go about solving the solution to find x of t. And so, like I said, we've got an example here. It's a mass spring system, so I'm not worrying about damping in this case. And here's my square wave, okay? So this is my forcing function. I've got my mass spring system, and this is the function I'm applying to it. What is the response going to look like? Now, in the notes, I have done the solution, written out. But what I'm going to do is, in the notes, the solution that I've written out, there's a few steps that I've sort of missed and things like that. And I thought it would help if I went through the whole solution on paper, use it with all the steps. So you can either take notes if you want to, or if you're sufficiently adept at following the steps that I've missed out, then by all means don't. It's up to you. So, but this is what I'm going to do. I'm going to go through the example here. And you can consider this as one of the worked examples that we go through at the end as well. Okay. So you've got a square wave. Let me go to the visualizer. So there's my square wave. This value is f0. This value is minus f0. Obviously this is 0, and here we've got t0, and here we've got minus t0. And minus t0. And that's f of t. Okay? The forcing function is a function of time. What's the period? What's the period of this function? 2t0. So t and so we could write analytically this function, okay? We've got f of t equals f0 when 0 is less than t, which is less than t0, and minus f0 when we have minus t0, t0. We could write that analytically, and then obviously we have to say that f of t plus 2t0 equals f of t. So that's how you write a function analytically. You say what the values are, and then obviously the period is 2t0, so you have to say that it repeats after every 2t0 seconds. So step one of the problem is to find the Fourier series for that function. Is that function even or odd? Odd. So that means there are sine terms only. So that means that an is 0. Is there a constant term? No. So that means that a0 is also 0. So we don't need to worry about any of the a terms. A, n equals 0 for all n. Okay? Bn, there are terms. So Bn, in fact, let's write out the Fourier series term. Ft is going to be, we've said that an is 0, n equals 1 to infinity of Bn sine so if we were to look at our solution, two pi n t divided by t. So that's our solution, because an is 0 and a0 is 0. So f of t has got to follow that form. Okay, t in this case is 2t0, so we can rewrite this as the sum n equals 1 to infinity of Bn sine, obviously we get n pi t upon t0, where Bn equals two over t, big T, integral minus t upon 2 ft sine of n pi t upon t naught dt. So let's stick in the period into this equation. So we have 1 over t naught minus t naught of f of t sine n pi t upon t naught dt. Now we know that f of t, as we said, is an odd function. Sine, we also know is an odd function. An odd times an odd is an even function. Therefore, you can write, this is 2 over t naught, between 0 and t naught. That's what's changed. F of t sine n pi t upon t naught dt. Okay? If you've got an even function, you can halve it. So between 0 and t naught, but multiply it by 2. Okay, so you can halve what's in the integral, but you need to multiply by 2. And that just eases the integration, because integrating something with, sticking 0 in is often a lot easier than having to stick a value in. So between 0 and t naught, what's the value of f of t? It's got a value of f naught, yeah? Between 0 and t naught, it's up there. Here. Between 0 and t naught, we've got a value of f of naught, so we can stick that into the solution. So we have 2 t naught, integral between 0 and t naught of f0 sine of n pi t upon t naught dt. This is quite an easy integral to solve, because obviously f of 0 is a constant, so it can come out of the integral. It doesn't make any difference to what's going on inside. And so we're integrating just the sine n pi t upon t naught term. Just this term is being integrated. And so if we were to do that, we could write, obviously this is 2 f naught upon t naught. What's the integral of sine? Minus cosine, okay. So we have minus cosine of n pi t upon n pi between 0 and t naught. So 2f naught upon t naught minus, so this is going to be cosine of n pi t naught divided by n pi Notice I've forgotten this term here. I'll rewrite it out here big so you can see what I'm actually referring to. Yeah. N pi t upon t naught. So we have minus cosine of n pi t naught divided by t naught divided by n pi divided by t naught. Then it's obviously minus a minus, so that becomes a plus of cosine of 0 divided by n pi divided by t naught. Cosine of 0 we know is 1. Okay. Now obviously these cancel, t naught and t naught there, so we have cosine of n pi. What's cosine of 1 pi? No. Minus 1. What's cosine of 2 pi? Yeah? Plus 1. So what we can do is we can take this out. This t naught cancels with this one, so we have 2 f naught divided by n pi. And then we've got 1, because that's gone, minus cosine of n pi. Now, this is b of n. When n is odd, sorry, when n is even, okay, we have cosine of n pi equals plus 1. So therefore, b of n, we've got a 1 minus 1, so that's going to be 0. When n is odd, cosine of n pi equals minus 1, therefore b of n equals 2 f naught upon n pi times by 2. Okay, so that's what's going on. And if you look at the solution in the notes that I've done, that should be what you get, yes. So those 3 steps in the notes on page 64, okay, that's it expanded essentially. We get to this solution. When n is odd, Bn has this value. When n is even, Bn is equal to 0. So if we were to write out that summation, if we go back to the equation up here, this equation here, we've got a value for Bn, and we can write that equation out, and that will be our value for the forcing function. F of t is going to be the sum from n equals 1 to infinity when n is odd only, so n is odd, of this term 4 f naught upon n pi times by the sine of n pi t upon t naught. Now we can simplify these things out. We could take the constants out of the sum. So that's going to be 4 f naught upon pi times by the sum of n equals 1 to infinity when n is odd of sine n pi t upon t naught divided by n. And if we know, since we know that the period is 2 t naught, t equals 2 t naught, okay, and that also equals 2 pi divided by omega n. sorry, omega. Yeah, sorry. So therefore t naught equals pi divided by omega. You can insert that into this equation. So we have f of t equals 4 f naught divided by pi n equals 1 to infinity of n being odd of sine n omega t divided by n. And then lastly, I'm going to make a substitution, n omega. That's obviously omega being the first harmonic, n omega is going to be the first, second, third, and so on, when n is 1, 2, 3, and so on. So I'm just going to replace n omega equals omega n, where omega 1 will be the first harmonic, omega 2 will be the second harmonic, and so on. And so I'm just going to make that substitution in here. We end up with 4f0 upon pi, sum of n equals 1 to infinity of n odd only of sine omega n t divided by n. So there's our solution. So that's solving the Fourier series for that square wave. Okay. And like I said, this is covered on page 64 in your notes, but not in such expanded form. Okay, are we all there? Looks like most of you finished writing almost. So in the presentation, like I said, ft is a period of 2 t0, so that omega is 2 pi upon 2 t0, so pi upon t0. Okay, since it's an odd function, all an terms are 0, all bn coefficients are. So this is going through the process partially, okay? We've got our bn terms, which is 2 upon t0 of the integral, okay, for n equals 1, 2, 3 and stuff. And we find that bn is 4 f0 upon n pi when n is odd, and we find that bn is 0 when n is even, okay? And so the function is going to be our constant term times by the sum of sine of n omega t upon n, because obviously we said omega is pi upon t0, where n is odd only. Then the next step is to replace n omega by omega n, omega subscript n, the frequency of the nth harmonic, so you can therefore write it like this. Okay, so there's our function. And so when n is 1, the solution for the forcing function is going to be 4f0 upon pi times by sine of omega, the first harmonic, t, and that's the forcing function. When n is 3, you have 4f0 upon pi times by sine of omega 3, so the third harmonic frequency, times by t divided by 3. And so on, okay, for n is 5, n is 7, and 9, and so on. And for each of those ones, for each of those values of n, you can solve for the value of x. Okay, so we can do that. Let's do that. So for each term in the Fourier series that is a sine term, you must solve the equation of motion to find the steady state response x of n to the nth harmonic input. Okay, so this is our function b of n times by sine of omega nt, where n is 1, 3, 5. Now that's the general form. When n is 1, obviously that's going to be b of 1 sine of omega 1 times by t. When it's 3, obviously you replace the n with 3, and so on. Now, from chapter 3, we solved an equation where that was the forcing function. We had f0 sine of omega t or whatever, okay? And if you remember, we have to apply a trial function that's in the same form as the input. And so our trial function looked a bit like this, okay? That's from chapter, this is all from chapter 3. Okay, where alpha and beta are coefficients to be determined, and omega n here is obviously the driving frequency. When n is 1, obviously it's the first harmonic. When it's 3, it's the third harmonic, and so on. So you've got to differentiate it twice to get the x double dot term. So you end up with minus m omega n squared times by x. Okay? And you can plug that into the equation. We get mx double dot plus kx equals the forcing function. So there's our m x double dot plus k times x equals our forcing function. And then what I've done here, this line here, I've grouped the cosine terms together. Okay? And I've grouped the sine terms together. Now, to equate this equation, this term must equal the cosine terms on the right-hand side. So that bit there must equal 0 in this case. And this whole term must equal the sine terms on the right-hand side. Since there is a sine term there, obviously this term here must equal b of n. So we can solve for alpha and beta. So the cosine terms must equal, the cosine coefficient must equal 0 because there's no cosine terms on the right hand side. Therefore alpha must equal 0 because k minus m omega n squared in this case is not 0. The coefficient for the sine terms must equal b of n. So we can solve for beta and we get beta equals b of n divided by k minus m omega n squared. Therefore, if you plug that back into our solution, we had alpha times by cosine of omega nt plus beta times sine omega nt. Well, obviously alpha is 0, so x of n is going to be b of n k minus m omega n squared times by sine of omega nt. That's the general form. Obviously when n equals 1, we have b of 1 times by k minus m omega 1 squared times by sine omega 1 squared. When n is 3, and so on. You can write out the sum of that with all the different terms in. But that's the general form. And then what you do, we've got a value for the x, our solution for that one harmonic, but then you have to find the solution to all of them and then add them together, and that's the superposition principle. And so if we go over that, x of t is the sum of all those x of n terms, and so it's that the constant b of n k minus m omega n squared times by sine omega n t. And obviously b of n we determined was 4f naught upon pi times by what was it? 4f naught upon n pi. On n pi, well the n has to go under the sum because that changes every time round. Okay, but you have the constant out the front, and there's the solution. Okay. So that's the solution of this problem. Now, let's just go over the steps that I went through to solve for this. In the first step, we used Fourier series theory to determine the Fourier series for the forcing function. Okay? And we determined the value for b of n. And we just found that when n is even, b of n is 0, and when n is odd, b of n equals 4 pi upon n pi. Sorry, 4f naught upon n pi. And so the forcing function looks something like this. A of n was 0, we found, and there's no constant term. So it's b of n sine omega nt. And obviously if we do the sum from 1 to infinity for n is odd, you end up getting these terms added up together, and so on until you get to n equals infinity. And we found b of n is 4f naught upon n pi. So for this term, we have 4f naught upon pi. For this term, we've got 4f naught upon 3 pi. For this term, we've got 4f naught upon 5 pi, and so on. In the second step, we solved the second order differential equation of motion with the trial function. So this is chapter 3 theory that matched our forcing function, resulted in this general term for our xpi, the steady state solution in x. Okay, for the different values of n. And so x of 1, when we take n equals 1, we end up with this term times by sine f omega 1t. Now if I replace b1 with what I know is b1, I end up with this term. Here I've got B3, here I've got B5, and so on, and you end up with these three terms. And so xt is going to be these terms added up together. Okay, which looks something like that. That's a constant term because that's the same in all of them. And then I've just got these these terms. And so that's my solution of xt. I add them up together, you get x of t, which is our solution. And if you can write that as a summation, and it looks like that. Okay. So step 1, find the Fourier series of the forcing function, if it's not already given to you. Step 2, find the solution for each one of those harmonics, for each value of n. And step 3 is add them all up together to get the complete solution. Is that clear? Yeah? Okay.